Hi students, it's Mr. Epperson. This video is on covalent bonds. After this video, you should learn that covalent bonds form between two nonmetals due to their electronegativity values. You should also learn that covalent bonds share electrons, and that valence electrons help us understand the covalent bond structures. So just to get started, the idea of bonds can kind of come into every day when you're looking at different types of substances that might look very, very similar but are actually quite different. Now, two of these look pretty similar and the other one maybe doesn't look so similar, but they all are crystalline or crystals. Like they have these facets that are shiny when they're, they kind of have a cut to them that reflects light, and the difference between them might not seem very great, but it's actually very, very pronounced, because at a molecular level what's happening is that you have different types of bonds responsible for these different substances. This one, I don't know if it's at the most obvious, but the one on the top left is sugar. Sugar cubes, right? Sugar, but this is called a covalent bond, or it's a covalently bound substance. This over here is table salt, sodium chloride, NaCl, and it is an ionic bond. And then this one at the bottom is actually titanium metal. And titanium metal is bonded in a way that we haven't learned and we won't actually quite learn much about, but it's called a metallic bond, and those types of bonds can still form crystalline structures even though there are no other types of atoms in there. Even if it's just the same metal in there, the same element, it can still form a crystal. But we still call that bond a metallic bond. So all these different types of bonds out there, we've learned a little bit about ionic bonds. If I just recap a little bit, ionic bonds is basically taking, the electron from one atom and giving it to the other atom, and giving it away because this atom over here, what we usually call the nonmetal, has such a high electronegativity value that this atom is going to steal or take the electron away from this atom, which has a low electronegativity value, and we call that the metal. So this type of atom here is giving it away. That's one type of bonding. However, there are other types of bonds out there, and the next type we're learning about is called a covalent bond. And in this one, the atoms actually share electrons between each other because they actually have similar electronegativity values. Essentially, what do you do when you have not just two types that are metals, but what if you had the two types that were both nonmetals? So just to walk it back a tiny bit from here, a bond is basically happening between two atoms when they move close to one another, and this is important, when they do not have stable octets already. So if you remember, an octet is that rule that you need to have 8 valence electrons in your outer shell. So 8 valence electrons in the outer shell, the outer energy shell. That's the octet rule. And that is very, very stable. Okay, so the reason the octet matters is because we're looking for stability. That's the goal. That is the goal of every atom, is to become stable. And what we mean by that, we mean it has a lower, sounds a little fancy and technical, but a lower potential energy. When we think about stuff having high energy, that seems like a good thing, right? Like we like to have energy to power our devices and stuff, or, to make our car go, or energy is a good thing and we're trying to get more of it. But actually the world and the universe wants to do the opposite. It wants to spread energy out as much as possible and not keep it contained in one little spot. And so the idea of energy being spread out throughout the universe is actually the goal of all matter. And when things form bonds, that's the process that's trying to occur. And so the goal is to lower that potential energy, or what we'd call instability, and obtain what's called a complete octet, basically 8 electrons in the outer shell. So that's the point of the octet rule and why it happens. There are two main methods for solving this. The main method we learned about is called ionic bonding, or stealing electrons is kind of our idea about that. And covalent, sorry, this should say bonding, which is sharing electrons. So we're going to learn about that one right now. The big deal with the different types of bonds is that electronegativity is driving the difference between these types of bonds. So we learned about ionic bonds because the electronegativity values between those two was very different. Let's take a look at this graph here. You have a graph where there's this sort of tall, sort of shown in 3 dimensions, where the elements over here are very, very, very tall relative to these ones over here that are very short. And the ones on the left being very short means that they have a low electronegativity value. Remember, that means how much does an atom want the electron? How strongly an atom holds on to an electron. And if electronegativity is low, it's going to be able to give that electron away pretty easily. If it's very, very high, like it is over in these elements on the side, which you notice, these are the nonmetals over here. Nonmetals over on this side. And those nonmetals on that side all have very, very high electronegativities. That's what makes them nonmetals. So if you bond a nonmetal to a metal, you're basically going to form an ionic bond. But if you form a nonmetal to a nonmetal, what happens? Well, again, just to draw this for you, which would be worth your time to put in your own periodic table, the electronegativity values actually increase from left to right and top to bottom, like I'm showing here. One thing to note, though, before we get too carried away, just because this area of the chart is very, very high in electronegativity, and those electrons want bonds very much, that doesn't mean that these elements over here in group 8 actually do anything regarding bonding. And try to remember why. The group 8, or what we call 8A, technically it's the 18th column, but this group is what's called the noble gases. And noble gases do not bond with other elements. The reason is because they have a complete octet. So if they have a complete octet, they're never going to bond with anything else, and we don't even consider their electronegativity values, though technically they are still very high, but we don't consider their values when we talk about bonding because they can't bond. They've already been fit, their outer shell is full, and they're extremely stable. They have low energy. And so you'll notice back in this graph, that whole column is missing. There's not even a column on this side. It's totally missing because it's irrelevant to bonding. They don't bond. So we kind of forget about that group on the side. But everything in this top right corner, besides those, is going to have a high electronegativity value, though don't forget about hydrogen. It kind of belongs with that group as well. Go back and I'll show you. Hydrogen is a 2.1, is pretty high electronegativity. So all of that considered, the electronegativity determines the bond. And if they, let's just basically put them into 3 different categories. If they're similar, those electronegativity values are similar and low. Let's say we're picking 2 metals, like we're going to pick this metal here and this metal here, bond them together, we're going to get a metallic bond. So a metallic bond will form if it's got similar and low electronegativity values. Again, we don't really consider this in our course, but it's important to know because it's one of the cases that can happen, right? So if that can be one case, what about if they have different electronegativity values? Well, we already have addressed this. Let's say we get sodium, that's this guy right here, I happen to know where it is, and then chlorine over here. Actually, that's fluorine, excuse me. So, well, that works too. Sodium and fluorine, if we want to bond them together, that's going to form an ionic bond because they have different electronegativity values. They're very, very different. However, and we'd call this a bond between a metal and a nonmetal. We've addressed that before. What if we have similar electronegativity values and they're both high? So what if I took, let's see, oxygen right here, or actually it's hard for me to look at this. How about, I think that's nitrogen and oxygen. Yeah, that'll work. So these 2 boxes, anyway, if I bonded those together, I'm going to get a covalent bond. And a covalent bond happens between 2 atoms that are both similar electronegativity and their values are high. And think about why this is. When they come into contact, they want to complete their octet, but they don't want to give up their electrons to do that. So instead, they kind of fight over the electrons equally, and they share them between each other. So that's really how we're going to define a covalent bond. It's going to be a sharing of electrons, but not of all the electrons, just sharing of the valence electrons. Hence the name covalent. Co meaning with, and valent, of course, meaning the valence electrons. So they have covalence, they have sort of co-ownership of those electrons, and they're sharing them. Now, when they make a bond from one atom to another, that bond is, there's a substance to it, and the bond is made out of the electrons, but not just any number of electrons, a pair of electrons. 2, actually, in total, in one from each atom. So I'll give you some examples of this in a moment. And when I show the bond, it's going to be represented as a line, like a dash between the two. You might have seen this before if you've seen chemical structures. And then the number of bonds, this is going to be a little tricky right now, but I'll show you how it works, is basically found by this equation here, which is 8 minus the number of valence electrons to tell you how many bonds something can make. So I'll go into that when you see it right here. So we have 2 atoms that are going to try to complete their octet and gain stability. When they find each other, they start to bond. And what they're going to do is they're going to share valence electrons between them and form a bond. Okay? Now, I drew a line to show the bond, but you might ask, well, like, is that it? Is that all that needs to happen? Are they good to go? Or do they need to, was that enough to form an octet, or do I need more electrons? The way to know if this has achieved stability is really to count the number of valence electrons first, and then we'll kind of go from there. There's actually a larger process to this that another video is going to cover. But to be more general, first I'm going to just think, how many valence electrons does fluorine have? Well, if I go back to my periodic table, it's in group 7, so it has 7 valence electrons. Now, I said that there's a little equation here. If I go 8, which is a complete octet, and I minus the number of valence electrons, I'll find out how many bonds it can make. 1 bond. So fluorine can form 1 bond, and let's draw that there between it and chlorine. Let's see how many bonds chlorine can form. Chlorine is also in group 7. It's just 1 period down from fluorine. So 8 minus 7, unsurprisingly, is also 1 bond. And now chlorine can form 1 bond. Now, does that mean that it forms another bond on top of it? No, not actually. Okay, it's not going to form another bond on top of it, but what it's going to do instead is it's going to form a bond just like it formed with fluorine. It's going to share the bond that fluorine formed with it before. So that's actually the sharing that we're talking about. It's sharing the bond, sharing the electrons that are the bond, and that counts as its own bond as well. So there's 1 bond from fluorine and the other bond from chlorine. We'd call that a bound and a satisfied molecule, one that's got its octet rule fulfilled. Another way of showing this is by drawing what's called Lewis structure. And again, as I've said, this is going to be an entire other video on how to do Lewis dot diagrams for covalent bonds. But what I'll just do right now is give a basic outline of how it works. I'm drawing all 7 valence electrons around these 2 atoms. And just for purposes of showing you, what's going to happen is these 2 electrons here that are sort of on their own, one atom and the other atom are going to share this pair, and that's going to cause the bond to form. These electrons up here don't really get involved in the bonding. They're sort of just on their own, but these electrons are in the bond themselves, and they form that bond. Okay, so let's try another example and see if it helps. I'm going to look at oxygen, and oxygen has, and chlorine again. So oxygen has 6 valence electrons. And if I remember that equation, it's 8 minus the number of valence electrons equals the number of bonds. Now this one forms 2 bonds. Chlorine, we remember, forms 1 bond. So if something forms 2 bonds and the other forms 1 bond, well, I can do 1 bond certainly between those 2. There's the bond for chlorine, but how do I make a bond between chlorine and oxygen that's going to go somewhere else, that I've run out of space, essentially. This is not going to work. And basically, that's the answer, is that this atom, these two atoms cannot simply bond together and form a complete covalent bond on their own. They won't make a valid molecule or a stable molecule. Instead, the way that I'm going to satisfy the octet rule, at least for oxygen, though chlorine is satisfied, oxygen is not still. I'm just going to bring in another atom, and in this case, just another chlorine. And I can make another bond between that one. And in this case, I've made a complete octet for oxygen, I've made a complete octet for chlorine, and this chlorine. Now, this is a different molecule, but essentially what I'm trying to show is that covalent bonding has rules, and if you don't follow those rules, you can't make a molecule. So with covalent bonding, the rules are very clear and pretty strict, and if you don't have the right arrangement of bonds, then your molecule just straight up won't work. So here's a final case for our consideration, and that's bonding with the element hydrogen. Hydrogen bonds all the time with covalent bonds, and it's kind of a special case. Chlorine, we know, forms one bond because it's in group 7, and we got that number from going 8 minus 7 equals 1. However, hydrogen, it's best to remember as a rule, also forms one bond. Why is that? Well, 8 minus 1, which it has 1 electron, is the first element, it has 1 proton, 1 electron, is 7. So does it form 7 bonds? No, it does not form 7 bonds. It forms one bond because it only has 1 electron. And that's the best explanation for it. Save for the other explanation, which would be that if you remember, that outer energy level that hydrogen has is that special one that only holds 2 electrons in it. It's a maximum that it can hold. And then you have to move up to the next energy shell. And if you minus the valence electron from that, then you get 1 bond. Now, whether or not that is making sense to you or not, the best thing to remember is just that hydrogen forms 1 bond. If chlorine forms 1 bond and hydrogen forms 1 bond, well, there you go. It's made its bond. And this is actually the molecule HCl, which is hydrochloric acid. And that's an acid that is formed in your stomach right now. Hydrochloric acid helps break down food. So in the end, did you learn that elements that are nonmetals will share electrons to form covalent bonds with each other? And that covalent bonds form because they have similar electronegativity values? And that bonds contain 2 electrons, 1 from each atom. And lastly, the number of bonds that are existing between atoms is based on the formula 8 minus the number of valence electrons, except for hydrogen, which always just forms 1 bond. Hope that was helpful.